The challenge of measuring tornado strength. Unlike hurricanes, which can be tracked for days over the ocean, tornadoes are small, short-lived, and extremely unpredictable. They form quickly and can last anywhere from a few seconds to more than an hour. Because of that, scientists rarely get direct wind speed readings inside them. Instead, the strength of a tornado is determined after it happens, based on the damage it leaves behind. When a tornado touches down, survey teams from the National Weather Service and research groups head to the scene. They look at destroyed homes, trees, cars, power poles, and other structures. The type and extent of this destruction tell them how powerful the winds likely were. The original Fujita scale, 1971. The system for rating tornadoes started in 1971 with Dr. Tetsuya Theodore Fujita, known as Mr. Tornado. He developed the Fujita scale, or F scale, which classified tornadoes from F0 to F5 based on the damage they caused. F0 tornadoes cause light damage, broken branches, damaged signs, maybe a few roof shingles. F3 storms destroyed entire houses. F5 tornadoes, the most extreme, could sweep well-built homes off their foundations and turn cars into deadly missiles. Fujita's system was groundbreaking, but it wasn't perfect. It relied heavily on damage interpretation, not direct measurements. For example, two tornadoes could destroy different types of buildings in different ways, yet be rated the same. The Enhanced Fujita Scale, 2007 update. To improve accuracy, meteorologists updated the system in 2007 to what we now use, the Enhanced Fujita Scale, or EF scale. This new version includes better data on construction materials, building quality, and structural engineering. It provides more detailed damage indicators and degrees of damage for different objects like homes, schools, trees, and even power poles. This update helps prevent overestimating or underestimating a tornado's true power. For instance, an old, weakly built house might be completely destroyed by an EF2 tornado, while a well-constructed building could survive an EF3. The Enhanced Fujita Scale accounts for those differences. The 6 EF categories explain. Here's how the EF scale breaks down. EF0, 65 to 85 miles per hour. Light damage. Broken tree branches, shallow-rooted trees pushed over, minor roof damage. EF1, 86 to 110 miles per hour. Moderate damage. Roof stripped, mobile homes overturned, windows shattered. EF2, 111 to 135 miles per hour. Considerable damage. Entire roofs torn off houses, large trees snapped, vehicles lifted. EF3, 136 to 165 miles per hour. Severe damage. Entire stories of houses destroyed. Trains overturned, cars thrown through the air. EF4, 166 to 200 miles per hour. Devastating damage. Strong houses leveled, cars thrown hundreds of yards, steel-reinforced buildings seriously damaged. EF5, over 200 miles per hour. Incredible damage. Strong, well-built houses completely disintegrated, debris carried for miles, even ground scouring. An EF5 tornado is so violent that it can erase entire neighborhoods, leaving nothing but bare foundations and scattered rubble. Using damage indicators. The Enhanced Fujita Scale uses 28 damage indicators, including things like homes, apartments, schools, shopping malls, trees, and towers. For each type of structure, there are multiple levels of destruction called degrees of damage. For example, a small home missing part of its roof might indicate an EF1. A home completely destroyed but still attached to its foundation might suggest an EF3. A home completely swept off its foundation usually means an EF5. This method helps scientists maintain consistency when rating tornadoes, even across different areas with different building standards. Why wind speed isn't directly measured? You might think scientists could just point a wind gauge at a tornado, but it's not that simple. Most instruments can't survive the extreme winds and flying debris inside a twister. Only a few specialized mobile Doppler radars, like Doppler on wheels, can safely measure wind speeds from a distance. Even then, those readings don't always match the ground-level damage because tornadoes can vary in strength across their width and height. That's why the EF rating focuses on damage. It's the most reliable indicator of what people actually experience on the ground. The role of aerial and satellite surveys. In recent years, technology has improved how experts measure tornado damage. After a major tornado, drones and satellites are used to capture aerial images. These help identify the tornado's full path, which can stretch for dozens of miles. Aerial views also reveal details missed at ground level, like subtle wind patterns or areas where the ground itself has been scraped bare, a hallmark of an EF5. This combination of ground and aerial surveys creates a much clearer picture of what happened. The cost of damage doesn't equal strength. One common misconception is that the cost of damage equals tornado strength. That's not true. A weak EF1 hitting a city can cause billions in damage, while a powerful EF4 in an open field might destroy only a few barns. The EF rating isn't about money. It's about wind speed and physical destruction. That's why experts carefully study the types of structures hit, rather than focusing on insurance losses. The long-term data and research. A database contains a record of each and every tornado that has been rated by the National Weather Service. The records are analyzed by researchers in order to hunt for patterns, such as which places experience the highest number of EF3+ tornadoes, or how the standards for buildings affect the survival rates. Over time, this data contributes to improvements in both safety and forecasting. As an illustration, research has demonstrated that tornadoes with a rating of EF3 or greater frequently hit during the night, which is more frequently than was previously believed. It is via insights such as these that alarm systems and public awareness may be improved. Famous examples of high-rated tornadoes. A few tornadoes stand out for their destruction and scientific importance. The 1999 Bridge Creek Moore tornado, Oklahoma, recorded winds over 300 miles per hour, the highest ever measured. The 2011 Joplin, Missouri tornado was rated EF5 after wiping out nearly a third of the city and killing over 150 people. The 2013 El Reno tornado, though it caused less destruction, was a record 2.6 miles wide, the largest ever observed. Each of these storms helped scientists refine the EF scale and better understand how extreme tornadoes behave. The future of tornado rating. In order to measure the severity of tornadoes in real time, rather than after they have already occurred, researchers are now researching on. Recent advancements in radar technology, drones, and even models based on artificial intelligence are assisting in the estimation of wind speeds and damage patterns with greater precision. Since radar has occasionally identified winds that are greater than 320 miles per hour, there is also discussion over the possibility of revising the EF scale once more in the future. This might involve expanding it beyond the EF5 level to include even more powerful occurrences. Why understanding tornado damage matters. When it comes down to it, determining the extent of damage caused by a tornado is not just about science, it is also about preserving lives. Through each EF rating, engineers are able to construct homes that are safer, emergency planners are informed, and communities are able to better prepare for the next storm. Through the study of the scars that these storms leave behind, we are able to improve our ability to forecast and survive them. The enhanced Fujita scale does more than merely categorize destruction. It also tells a story about the power of nature and the continual efforts that humanity is making to stand against it.